Okay. Okay, we are now recording. So let's go from current slide. Before we get started on that, let's do a quick, let me just make a few minor announcements. Number one, believe it or not, Friday was a great day at the office because nobody else was in the office, so I could get a fair amount of grading done. People did come by, so there were interruptions, but I got a fair amount of grading done and was able to get some more done over the weekend, especially yesterday when the weather was so rotten or cold or rainy that I got some stuff done. So my stack is down to that. It was much, much bigger last week, so I did get some. And I would have gotten, I think, even that finished, except yesterday afternoon, my red ink pen ran out of ink, and I could not find one anywhere in the house to replace it. So I quit grading and went to putting grades on Blackboard. So your grades, the ones up to the point of where my red ink ran out, those are all on Blackboard now, okay? And my other classes as well, except the morning classes this morning. For some reason, I think I know what happened, but I managed to skip those inadvertently. So Michael's here. So I will try to get the rest of those caught up. Some. I don't know how much time I'm going to have tonight because I get home so late. Doubt if I'll get much tonight. And tomorrow I've only got 2 hours of office hours. My big day Monday, of course, yesterday was a holiday, so I didn't get my 4 hours of office hours in that. Okay, so anyway, I did get that done. But then there is some more good news, bad news situation. Next week, believe it or not, is Thanksgiving week, okay? And Thanksgiving, of course, is a state holiday. But the bad news for you guys is you got the whole week off. We have to be here at meetings Monday, Tuesday, and Wednesday, but you get the whole week off. There are no classes next week, so sorry about that. I hope you can live without it and through it, okay? Yeah, okay. So, where we are in the class right now. We're in Chapter 4. We finished Chapter 3 early last time, so we did get a fair amount of 4 done last time. We got enough to have the first lab done. And depending on how fast we can go in these next couple of hours, if we get far enough, we might be ready for the second lab, okay? Doubt if we'll finish the chapter, but if we get enough for the second lab, the first 2 hours are in class. Next 2 hours, if we get enough covered, will be in lab. And it's going to take me a little while to set this one up because they were having some type of lab, reports or something like that in there. So I really couldn't do a lot towards setting up the lab before class. But I got all the material down there. It's just going to take a while to set up. So, but the lab isn't going to take super long to do. It'll probably take me almost as long to set up as it will for y'all to do it, but not quite. You'll spend a little more time on that. Okay. And then the last 30 minutes today will be the Chapter 3 test, if you're ready for it. I know some people have been out a lot, and if you don't feel ready, you can certainly take it later, anytime during my office hours. Okay? So that's how we'll try to go today. 2 hours class, 2 hours lab, 30 minutes test. Now, if we can't get enough covered in the 2 hours class, it'll be a 4-hour class. So let's see what we can do on that. All right. Any questions on anything we've done up to now, especially Chapter 3 questions if you're studying for that for the test. Now, if you did get yes.
I have a question. It's because I'm dumb, I guess, but on page 65 in the book.
Okay, wait just a second. Let me mark the metric here while I'm thinking of it. What page in the book?
I'm going through remedial algebra now, and I think maybe I'm missing something.
Okay, what page?
65.
65. Okay. 60.
I think maybe this is algebraic
Right.
depths that.
Okay. Okay. I'm on page 65 then. What?
Yeah, I can show it to you.
Okay.
Maybe I'm sure you discussed this in class,
Okay.
but it's this.
Right.
And it was puzzled. Multiply this times that. That's mass. Is that not?
No,
is that 5?
No, that's meters.
Oh, that's meters.
These are just units there. Meters per second squared.
Okay. Well, that's what.
See, they separated the units from the numbers. See, 5 kilograms, that's the mass. 9.8 meters per second squared, that's the acceleration due to gravity. So then they pulled the numbers over here and put the units over here. It's sort of dumb.
Well, I kind of got lost from here to this state.
Yeah, well, you see, 5 times 9.8 is 49.
Right.
Right? And then they combine the units, kilogram meter per second squared, that is a newton. Yeah.
Yes. Okay.
Mass times acceleration is a newton.
Just
It's force. Right.
A little slow on the
Yeah,
draw.
no problem. I thought that was a strange way of doing it. I didn't even mention that because I thought the way they did it was confusing. So I didn't even mention that in class. Okay. All right. Picking back up where we are now is Chapter 4, page 95, top of the second column. Okay, I believe this is the slide we basically got to and maybe just about got started on, but didn't get very far. So what is heat? They've given us a definition, slightly varying different definitions over the last few slides. Well, here's one. A measure of the internal energy that has been absorbed or transferred from or to another object. Okay? So if you remember, heat, I talk about it as if it's thermal energy. And in a sense it is. But heat is thermal energy that's being transferred from one object to another. Okay? For instance, having the window open back there is letting some of the heat in the room out of the room, so that's heat leaving, and letting some cold air in, which is heat, lack of heat coming in. So that's a measure. Heat is a measure of the internal energy that has been absorbed or transferred to or from another object. Okay? Let's say we had last night my wife boiled some shrimp, okay? And it was still hot from the pot, but she wanted to go on upstairs, and I was still fiddling around downstairs and had to put the dog out and stuff. And she said, I'm not going to put this in the fridge yet because it's still pretty warm, but be sure to cover it and put it in the fridge before you go to bed. And so probably 15, 30 minutes later, I did it. Why? We were wanting the heat to transfer from the shrimp to the room rather than put it in the fridge and have it warm up the fridge. So that's heat. When there's a transfer, either absorbing or transfer to or from one object to another object, that's heat. Heat is not how hot something is, that's temperature. Heat is the transfer of thermal energy or internal energy. Okay? There's two related processes. These are really clever here. One is heating, okay, increasing the internal energy of the second object, or cooling, which is decreasing the internal energy of the other object. For instance, when I did put it in the fridge, it was still a little warm, not too much. It gave heat over to the refrigerator and warmed up the air in there just a little bit. But on the other hand, the refrigerator was cooling, decreasing the internal energy of the shrimp. Okay? And tonight it should be nice and cold. Okay? She's probably going to be enjoying it in just a couple hours. Okay? Now, what are some heating methods? Okay? Well, one way to heat something is, of course, to change its temperature. That is a transfer of heat to do that. We saw that in the lab last time. When you put the thermometer into the boiling water, it was sitting down around, 20 degrees Celsius, because that was room temperature, and you rapidly saw the liquid in the thermometer go up. That's one. Create a temperature difference. Energy catch this one. Energy always moves from higher temperature to regions to lower temperature regions. It doesn't move the other way. I can remember my dad saying, close the door, you're letting the cool air out. No, or in the wintertime, you're letting the cold in. I'll say it that way. You're letting the cold in. No, we're letting the heat out because temperature difference, the energy always flows from higher temperature to lower. Never the other way, okay? It always goes from a high potential to a low potential. Now, next chapter, when we're doing electricity, you'll see that's one time in physics when we consider things going in the opposite direction. That's a little bizarre. We'll talk about it then. But energy always moves from higher temperature, this is heat energy, to lower temperatures. So know when you have the door open, you're not letting the cold air in, you're letting your heat from the house exit. Cold air is coming in, but the heat is always going from high to low. Now, there is another way that we can move heat. And we saw this in the lab too, even though we hadn't covered this yet. No, this is yet another one, sorry. We'll get to the other one in a minute. Energy form conversion. Y'all do this every day. You did it when you drove here today. You took the heat from the burning gases in your cylinders and transferred that heat into doing work of turning the wheels of your car. You're doing that every time you're using a heat engine, every time you're using a heat pump. You're always transferring heat by doing work on something else. So there's two things that heat does. It can change temperature or it can do work. Okay? We'll learn other things a little bit later. So what are some of the measures of heat? Okay? This is on page 96. Okay? We got a bunch of different ways to measure heat. And they come from historical misconceptions, I would say. Way back, Aristotle had said there are 4 basic elements in nature. Okay? Air, water, fire, earth. Earth, wind, fire, and what was the other one I said? Water. Earth, water, wind, and fire. Okay? Now, 3 of those made a singing group back when I was younger, but y'all wouldn't know that. Okay? You wouldn't. Okay. All right. So anyway, way back then, so he had fire being an element. We know today fire is not an element. Okay? It's a transfer of energy. Okay? Or heat is. Okay? And energy is not an element. Earth is not an element. Water is not an element. And wind is not an element. Okay? So he was wrong on every count. Now, wind does contain some elements. Water contains some elements. Earth contains gazoodles of different kinds of elements. Okay? But he was wrong with that. But even as late as the time of Isaac Newton, and even past there, the early chemists, when they determined, no, there's way more elements than those, and those aren't even elements, they still counted this other one called caloric, which was their equivalent to heat, or Aristotle's fire, okay? And that's where we get one of the measures of energy. Now, this is considered a metric unit, a calorie, but it's not an SI unit, okay? This is one that was used way back when they thought heat was something very different from energy, okay? Didn't even consider it energy. They thought it was an element. So, and Lavoisier was one of the first to list a significant number of the elements. I think he got maybe 35 to 50 or so of them pretty close to right. had a few compounds in there that weren't really elements, but he didn't know how to separate them. And he also had caloric in there, okay, which was not an element. Now, a calorie is the energy needed to raise the temperature of 1 gram of water. Now remember, a gram would be, remember your little fingernail's about a centimeter across. So if you have a centimeter high, a centimeter wide, and a centimeter deep, little cube, like a tiny little sugar cube, that would be about 1 gram of water, okay? 1 degree Celsius. Now, a degree Celsius is a substantial degree, but it's not a lot of temperature change. So that's what a calorie is, the energy needed to raise the temperature of 1 gram of water, 1 degree Celsius. Why water? Most common material on the planet, surface of the planet anyway, okay? Now, because that turned out being such a small amount of energy, they started going to kilocalories, which is how many calories? Kilo means 1,000 calories, okay? Well, that got to be so common that they quit calling them kilocalories, especially the people who dealt with food calories. They started just calling them calories, leave off the kilo. Well, they were really talking about kilocalories. So for the food industry, a capital C calorie is a kilocalorie, which is 1,000 of the little c calories. I know that's strange, but it's true. Does anyone have, oh yeah, there's a Mountain Dew back there. Okay, is that diet or is that regular? Okay, check on it and see how many calories it is. Second? 240. Is it capital C or little c? Capital C. That's what they measure it in. Capital C calorie is actually a kilocalorie of 1,000 little c calories. The energy needed to raise the temperature of 1 kilogram of water 1 degree Celsius. That's quite a bit more. This book, I think, has a mass of maybe 1 to 2 kilograms. And if you had that much mass of water, it's going to take a lot more heat, 1,000 times as much heat, to raise it 1 degree Celsius. That's on the metric side. That's still not the SI units, though. Let's go over to the English side, which the English don't technically use anymore. And here's Brian, right? Yes. Okay. All right. They use the British thermal unit. And you probably are most familiar with this if you deal anything with air conditioning. How do they rate air conditioners? BTUs. Have you ever heard that? That's what they're talking about, British thermal units. Okay? The energy needed to raise the temperature of 1 pound of water, 1 degree Fahrenheit. Okay? Now, a pound is a whole lot more than a gram. I mean, a gram is tiny. A pound, you have a pretty good idea of what a pound is. A lot more water. Now, 1 degree Fahrenheit is just a little more than half a degree Celsius, but still, it's in the same ballpark. Whereas 1 pound is tons more, quite a bit more than 1 gram. However, 1 pound of water is less than 1 kilogram. A kilogram is about 2.2 pounds. So it's in the same ballpark, but a kilogram is more water. So it's 1 pound of water, 1 degree Fahrenheit. So BTU is less than a kilocalorie, but much more than a little calorie. All right. Now, finally at the end here, we get the actual unit. Because, see, heat is a transfer of energy. Energy's unit is not calorie in the SI, it's joule. And what's the mechanical equivalent of that? 4.1884 joules, that's all, more than 4 joules, is 1 little c calorie. So that's not much. That's a very small amount of energy, a joule. Generally, we deal with kilojoules or bigger, okay? So a joule is much smaller than even a little c calorie, way less than a BTU, and way, way less than a capital C calorie or a kilocalorie. So that's the mechanical equivalent of heat. And in the last chapter, we talk about James Prescott Joule, for whom it was named. He's the one who got the first good estimates of that equivalence. And the very careful and detailed experiments he ran, he was able to establish that equivalence there. Now, he followed another guy who is going to be at the end of the chapter. I think I'll wait to get to him. I think I just saw him, yeah. Count Rumford, Benjamin Thompson. So we'll hold off on him. He's the one who first showed that heat and energy were related, working energy. Okay, this is Trent, right? Okay. All right. So those are the different measures of heat. Little c calories, capital C calories or kilocalories, BTUs, and joules. All ways to talk about or measure heat. All right. Before we move on then, let's go back and do a couple of the, okay, we're going to go back several slides and have some brown space to work. And because this brown space, pick a color, one of the lighter colors. Yellow, all right? Orange, light green, what would you like? Second? Any? How about yellow? Okay. Here's example 4.4. Okay. A 1,000 kilogram car. What's that a measure of? Okay, that's not a can, it's a car. I can't write. Whoops. Okay. That's the mass of the car. Okay, the mass of the car is moving at 90 kilometers per hour. Okay, what's that a measure of? Speed or velocity. I'm going to put V because that's probably what we're going to need. Okay, now they also tell us, thank you very much, so we don't have to do the conversion, that's 25.0 meters per second. We could have done that conversion, but thank you for doing it for us. Okay, how many kilocalories are generated when the car brakes to a stop? Okay. Now, what did they just describe here? A car with a mass going at a speed. What kind of energy are we talking about? So kinetic, because it's moving. So what would be the kinetic energy of that car before it stopped? KE of the car would be, what's that formula? 1/2 mv squared. Plug in, that's 1/2. The mass is 1,000 kilograms. And velocity was 25 meters per second, but you got to square that. Okay? Well, half of 1,000 is 500, right? So 500 kilograms times, anyone know what the square of 25 is? 625, perfect. 625 meters squared per second squared. You square the units as well as the number. Multiply those together, and I believe that gives you 3,125,000. Okay. That's, and kilogram meter squared per second squared, what's that a measure of? Joules. I said joules was a fairly small quantity. It is. That was 312,500 joules is the kinetic energy of that car before you brought it to a stop. So when you hit the brakes, if you got regenerative braking, that's going to be doing something else. But if you just the plain old disc brakes, what you're doing is pressing a rough surface against another rough surface, right? And that's what brakes the car. Yay or nay? Okay? What's produced when you do that? A lot of heat. I hope you've never touched the brake pad right after it's brought in and come into the shop. If you did, you've got a burn, right?
The rotor's worse.
What's that?
The rotor's worse.
The rotor?
The rotor.
Oh, I bet so. Okay. So, different kind of friction there, but still friction. Okay? So that's what we want. That's how many joules of mechanical energy, kinetic energy that car had. If it brought it to a complete stop, where else was the energy going to go except to heat? Okay? So that's 312,500 joules. And the question here is, how many kilocalories are generated when the car brakes to a stop? Now, if you look just above the example in the book, you'll see that 4,184 joules is 1 kilocalorie. So we can take this and multiply it by a blank blank and equal a blank joules. That's what kilocalories. We're going to kilocalories. Okay. Kilocalories. Okay. Now, the blank blank here is for our conversion unit, conversion factor. This blank is for numbers. That blank is for units. Always put the units into place. What unit goes above the line? What goes below the line? Between joules and kilograms. What goes where? Anybody? So again, joules is downstairs. Okay. Putting kilocalories upstairs. Okay, and then right above the example in the book, it gives you that conversion. Now put the units to match with the numbers. 4,184 joules. 4,184 joules, and that would be 1 kilocalorie. Now the joules go out, and if you got your calculators handy, if you still got the 312,500 joules, divide it by 4,184 joules, and what do you get? Anyone with a calculator? Someone had one. Okay? Or abacus, or whatever you're using. How many kilocalories? 312? Oh, no. Yeah. 312,500 divided by 4,184. Say again?
74.7.
74.7 kilocalories. Okay? That would be, I want to say close to 75, but they probably leave you 74.7. Okay, that's how many kilocalories of heat are produced by the braking of that car. Now, anyone have a good idea how much 90 kilometers per hour is? Is that pretty close to 60? Fairly close? Ballpark? Okay, let me think. 0.6. Yeah, 54. I believe that's 54. Somewhere right around there. Right?
125, 60.
I'm sorry?
125, 60 miles per hour.
Okay. Yeah. If you multiply that by 0.6, that'd be about 54. Okay, about 54 miles per hour. Okay? Now, if you think back on this, okay, 75, let's just say 75 kilocalories of heat. The energy that you got from drinking your Mountain Dew back there, what was that again? 340? 240. That was enough to stop close to 5 cars. The energy that you are drinking from that, believe it or not, is enough energy to stop about 5,000 kilogram cars. That's about 2,000 pound cars, 2,200 pound cars, in fact, 1 ton cars going at about 54 miles an hour. Okay. You sure you want to drink that? No, never mind. Okay. Y'all can afford it. I can't. Okay. Okay. So you see, kilocalories is a much bigger unit, but still not as much as it was consumed by one bottle. Half a bottle, a quarter of a bottle of the soft drink. Okay. Unbelievable, but true. Okay. The temperature increase from that amount of heating could be calculated from equation 4.4 if you go, where is the 4.4? We should have already covered it. No, we haven't. That's coming up. I was going to say, I don't recall doing that. Okay. All right, any questions on measures of heat? There's only the one example there. They usually have two, but they only had one there. All right, let's move to specific heat. Now, going back to what we said before, when you're heating something, one thing you can do is change its temperature. But like we saw in lab last time, something else sometimes changes. Well, no, okay, I'm sorry, I'm jumping ahead. So let's deal about the variables involved in heating something. Okay, certainly, anytime you're adding heat to something, not every time, but a lot of times, you're changing the temperature. So the temperature change is going to result in adding heat or taking heat away from an object, right? Okay? Now, we also saw when we talked about the bathtub full of water and the thimble full of water, the mass makes a big difference too, right? So the mass is also involved. But then the other thing is the type of material, okay? Different materials often require different amounts of heat to produce the same temperature change. Now let me give you a sort of an illustration that I actually was a party to. Used to be, I don't know if they still do it or not, but every winter there would be a weekend that they set aside, and because there's usually only one physics instructor at each community college, you really had no other one else to deal with. You could deal with some with the math instructors or something. Most of the time they taught both subjects, but you never got to hang around other physicists, okay? So what they started doing was having a meeting every winter, usually in February, at some location in the state, and all the physics instructors that could go would go to that meeting, and you know they have papers and make presentations. This one time we went to this place, a really nice location, and this one team had brought in some experiments they did. So I'm going to try to describe it to you. It had a metal plate, probably about that big around, metal plate, and it was probably less than an inch thick, but had some thickness, the whole plate. And they had drilled, it seemed like 6 or 8 holes into the plate, okay, the edges of the plate, okay. Now, they had pegs that would fit firmly into those holes, okay. Now, the pegs were made out of different metals. I remember they had aluminum one, they had copper one, they had an iron one. I can't remember all the metals they had, but they're all, regular metal. No silver or gold pegs, unfortunately. Just regular old metallic pegs. They wouldn't have kept them too long if they had them. So what they had, you just chose a peg, any peg you wanted to. So 6 of us chose pegs, or 8, whatever it was. And then they said, what we want you to do is pick your hole and plug your peg into the hole. Well, they had a Bunsen burner. You know what that is, a little flame underneath. So underneath the plate, and it was heating up the plate. And you were to put your peg into the hole and hold it there as long as you could. Okay? And after a fairly short while, if I'm not mistaken, the copper guy let his go. Now, was he just a wimp? No. Not necessarily. Okay? Then somewhere else, the aluminum guy let his go fairly quickly, and then it went all around. And the reason was different materials require different amounts of heat to produce the same temperature change. They were releasing on a temperature change, not amount of heat change, because the heat was different for each one, because there is that difference there. The measure of that different amounts of heat to produce the same temperature change is called the specific heat of that material. And that is remember we said density was unique to a material. If you had 5 pounds of copper or had 5 tons of copper, the density of copper is always the density of copper. The density of iron is the density of iron. And they are very different from each other. No matter how much or how little you have, the density is a characteristic number for that material. Well, specific heat is also. Okay? Summarized by one equation, and I don't know if they're going to give you the equation yet, not yet. Here's an example. Here's 10 grams of aluminum at 20 degrees. It takes 176 calories, heating that up, 176 calories to produce 10 kilograms of 100 degrees aluminum. So to raise it 80 degrees, it took 176 calories. It also takes exactly 176 calories to cool 100 degrees Celsius block of aluminum to 20 degrees Celsius. Okay? Now, 10 grams of copper, because copper is much denser, it's going to be a smaller cube, but if you same 10 grams, it only takes 74.4. So that copper guy let go really fast because he only had to absorb 74.4 calories from that Bunsen burner to bring it to boiling point, and that would have burned his hand before he got there. So, yeah, he let go way before the aluminum guy did, because it takes more than twice as much heat to change copper from aluminum from 20 degrees, 10 grams, okay, to 100 grams, 20 Celsius to 100 degrees Celsius. If we had a gold peg, that would have been one of the first ones. No matter how much you want to hang on to that gold, you couldn't do it because it only took 24 calories to bring that up to 100 degrees, which would burn your finger. You know, your skin will burn at 100 degrees, okay? You'll get a blister there, okay? And that would have only been 24, a third of the amount that it takes copper, and goodness gracious, a seventh of the amount that it would take aluminum, maybe less than that. Yeah. So, different materials have different specific heats. Specific heat for gold, 0.03 calories per gram degree Celsius, that's what that is. For copper, 0.093 calories per gram degree Celsius. Okay, that's more than 3 times as much. And then for aluminum, 0.22 calories per gram degree Celsius. That's another more than twice that. Okay. So that's decreasing heat capacity as you go down. Now, one thing, this isn't always the case, but you'll sort of get the idea. Copper is a lot denser than aluminum, and gold is a lot denser than copper. Guess what? That's the direction there. The molecules are closer together. They're denser. Okay, they're also bigger, heavier molecules or atoms. So that all has to do with specific heat. Well, what's that one equation? Here it comes. And in this chapter, capital Q stands for heat. The lab we do, if it's today or Thursday, whenever we do it, that's going to be something we'll be measuring. M is the mass. There's the mass. C is specific heat. There, that's the type of material. Delta T is the temperature change. Delta meaning difference. T final minus T initial. T final minus T initial. All three of these, same temperature change, 80 degree temperature change, all had the same mass, 10 grams, 10 grams, 10 grams. What changed with these were the specific heat. Does that make sense? And that is something we'll be using in today's lab, if we do the lab today. Hopefully we will. All right. I think we will. But before we get to heat flow, by the way, that is the equation 4.4, which you could go back and check in your the previous example when we talked about you can convert this kilocalorie where is it? No, the temperature increase from this amount of heating could be calculated from equation 4.4. Okay? There's something else you'll need to know before you can use 4.4. Okay, let's go back to it and see. You know the temperature change. No, you know the heat, Q. We need to know the mass of the plates, of the brake pads and stuff. But you'd also need to know their specific heat. And frankly, I don't know what that is. So you could, if you had that information, determine what temperature changed, but you can't with the information they gave you. All right, just to make a correction there. All right, so let's do example 4.5. Okay. All right, we'll put it here. How much heat, what variable do we use for heat? Capital Q. This is the unknown. How much heat must be supplied to a 500-gram pan Thank you. Thank you again. All right. A 500-gram pan, what's that a measure of? Say again? That's the mass of the pan. Okay. To raise its temperature from 20 degrees Celsius to 100 degrees Celsius, so 20.0 degrees Celsius to go to 100, is that also 0.0? Yeah, 100.0 degrees Celsius. What does that represent? Okay, and what would that be?
Delta T.
How much?
Delta T.
Delta T, but how much is that? 80. So that'd be 80.0 degrees Celsius is your delta T. Temperature change. If the pan is made A, out of iron, okay, I'm just going to call it Fe, that's the symbol for iron, and B, if that's made out of aluminum. Okay. Now, not enough to tell us that until you turn the page. And if you turn the page there, you'll see that there is a table 4.2, top of the page there. I don't think this shows up in the slide set, so I'm going to just point it out to you here. Okay, I know this won't be projected or anything, but you'll see. Here is the substance here, air through water, okay, alphabetically, which is strange to do it that way. The specific heat of selected substances. Now, air is a mixture, but just generally air, normal temperatures and pressure, that would be about 0.17 calories per gram degree Celsius. Okay? Aluminum, 0.22, we saw that in the earlier slide. Concrete, the walls over there, approximately 16, so it's not much different from the specific heat of air, 0.16. Copper, 0.093, we saw that on the previous slide. Glass on average, 0.160, so the glass and the concrete blocks have about the same specific heat. Gold, we saw that was 0.03 from the previous slide. Ice, you would think that would have a high or low specific heat. Okay, sure enough, 0.5. Larger than aluminum, gold, copper, any of the others, just about. Iron, 0.11. That's less specific heat than glass or concrete or aluminum. Pretty low. Okay. Lead, 0.0305, almost as low as gold. Mercury, 0.033, just slightly more than lead. Seawater, high or low? Specific heat. 0.93, that's pretty high. The highest yet so far, even more than ice. Soil on average about 0.2, so that's be pretty close to what aluminum is. That's 0.22. Steam, 0.48, just below what ice is. But then water, high or low? High. It's 1.00, and of course, if you think about it, that's the definition of a calorie. A calorie is the amount of heat required to raise 1 gram of water 1 degree Celsius. So guess what? Water is exactly 1.00. Okay? So it's about the highest specific heat of any substance on the planet. I think helium is a little more, but that's not very common. Yeah, what you got? Question?
Yes, sir. Ice
Yes.
is 0.5 and water is 1.
Right.
Ice has air in it? Is that what it is?
No, it's just that the crystal structure of ice is different from the structure of water. Water has no crystal structure, and it just takes more heat.
Is it the density?
No, density is actually less dense than water, but not by a lot. So yeah, those things are all contributing to it probably, but it's not quite the same. Now,
Seawater's got salt in it. So
yeah, and that actually decreases its specific heat
0.9
just a little bit. But it's the next closest thing to water. Now, for you guys, what's an application of that you use all the time? That water has one of the highest specific heats of any material known to man. Naturally occurring, certainly.
What do you ask?
Okay? Well, where would you take advantage of that? And you do take advantage of it every day. What's your coolant for your car? What's in your radiator? Yeah, okay. You put ethylene glycol in it because you want to keep it from freezing when it gets below 32 degrees Fahrenheit. But guess what? Water has the highest specific heat, so therefore the best material in the world to take excess heat away from your engine is going to be water, because it has the very highest specific heat of any known substance. Anything else, yeah. It's better than the aluminum block, the iron block, the steel block, anything. Water is the best remover of heat because it has such a high specific heat. Here's Melanie. All wrapped up for winter, right? All right. All right. So with that table in mind, we can go back and answer the question that we had. How much heat is where is the problem? I've lost the problem. How much heat must be supplied to a 500-gram pan to raise its temperature from 20 degrees to 100 degrees water? Now, what's those temperature ranges? 20 to 100. What's 20 degrees approximately? We did this earlier in the chapter. It's room temperature. Very close to it. 68 degrees Fahrenheit. That's probably not far from what this room is right now. 20 degrees Celsius. What's 100 degrees Celsius? Boiling point of water. So here you're wanting to boil your beans or whatever you happen to be cooking. So how much energy is it going to take to warm the pan, not the water, the pan from 20 degrees to 100 degrees? It's a very practical question if the pan is made out of iron. Okay? So how much heat would be required for that? So we're looking for Q for iron. And what's the formula? MC delta T. The mass was 500 grams, 500.0 grams. Now, the C for iron. From the table we just looked at, what was C for iron? 0.11. 0.11, and that was calories per gram degree Celsius. I like to put a dot for the multiplication there just so it'd be easier to find. GC doesn't mean a lot to me, okay? And what was our delta T? Unfortunately, I can't write there. Let me write it over here. What was that? 80 degrees Celsius. Okay, we had to jump way over there to get our, and it's 80.0, but that's okay. All right? Now, if you got a calculator, do it. It's not that hard to do. 500 times 80 would be 40,000 times 0.11 would be 4400, And notice what happens. The grams go out, degrees Celsius goes out, and that leaves you calories. So I got 4,400 calories. Is that what y'all got? 4,400 calories. Now, if you wanted a smaller number but a bigger unit, what could you use? How many? How many? 4.4 kilocalories. Oh, I don't have to spell it. I'll put the briefing. KCAL. Let me clean that up a little bit. Okay. Kilocalories. KCAL. Okay? Now let's do the same for aluminum. The heat required to heat that aluminum pan, same amount, same mass of a pan, 500.0 grams. What's the specific heat for aluminum? 0.22 calories per gram degree Celsius times the same temperature change, room temperature to boiling point of water, 80.0 degrees Celsius, okay? And again, the grams go out, degrees Celsius goes out, and that would be 4,000 times 0.22 would be 8,800 kilocalories. Okay? Calories, or 8.8 kilocalories. You could have just doubled the answer. I was going to do that, but I was afraid you would think somebody might think they could always do that. You can't. It's just that the specific heat of aluminum happens to be twice that of iron. Okay. Now, here's the deal, folks. What does that mean for you? That cast iron pan is going to heat up a lot faster than that aluminum pan. If it's the same mass. Now, aluminum is a lighter metal, so your pans are a little bit lighter, so you have all that going into the problem as well. But, usually, and that's one reason cast iron cooks so well. Nice, even thing. All right. Make sense? And if you'll notice, your answers there are 4,400 calories, which is 4.4 kilocalories, or 8,800 calories, which is 8.8 kilocalories. Okay. Then they have example 4.6. Okay. Different problem, so let's erase this. And 4.6, top of the first column, page 98. What is the specific heat? What symbol do we use for specific heat? C. So this is what we're looking for now. That's a little c, which is a parameter. Don't confuse it with a capital C, which is degrees Celsius. That's a unit. This is a parameter. C. That's yes in Spanish. Okay, never mind. Okay. What is the specific heat of a 2 kilogram metal sample? So 2 kilograms is a measure of what? That's the mass of the metal. Okay. If 1.2 kilocalories is required to increase the temperature from 20 to 40 degrees Celsius. 20.0 to 40.0 degrees Celsius. Okay, what's that represent? Okay, that's your delta T, and how much? 20.0 degrees Celsius. Okay, so now we're looking for C. That is the specific heat of the unknown metal. So let's see what it turns out to be. What does the 1.2 kilocalories, what does that represent? That's your capital Q. Okay, I think we got everything we need. Now let's see. I'm going to scroll ahead a little bit. All right. This equation is set up for you're trying to find the Q. If we're trying to find C, which is what we're wanting to do, we can either adjust our equation now and then plug in the numbers. I call that chug and plug, or we can put the numbers into this equation and then move the numbers around. I call that plug and chug. You can call it anything you want to. Which would you rather do? Adjust that for C, or, okay, let's do that then. What would that be? How would you isolate the C? Divide both sides by M delta T. Divide both sides by M delta T. That way the M's go out, delta T's go out, and you're left with C. So let's go back here, and we'll do C is equal to, why did that not show? Okay. C is equal to, yeah, I guess I just didn't write down Q. Okay. Q over M delta T. So what's your Q in this case? 1.2 kilocalories. And your mass was 2 kilograms. And your change of temperature was 20 degrees Celsius. Okay? Now, just a little hint here about using your calculators. Though you really don't need them, but I think it would be pretty easy to do it. If you do 1.2 divided by 2, that's 0.6 by the way, and divide that answer, you don't need to do. Now, if you are tempted to put a time sign there, what you better do is open parentheses before you write down the 2. Because you need to do this as a unit before you divide into that. So the easy way is 1.2 divided by 2, and that answer divided by 20. That's the easiest way. Or you do 1.2 divided by, open parentheses, 2 times 20, close parentheses equal, that'll give you the same answer. It's just a lot of, a few more keystrokes. 2 more keystrokes that way. Anyway, do it however you want to, and what you get is an answer. 0.03. Okay. 0.03. What units? Kilocalorie per kilogram degrees Celsius. Now, if I'm right and look it up in my table, what's that pan made of? That metal sample. It's not a pan. That metal sample. Gold. Okay. If you got 2 kilograms of gold, I want to be your friend. Okay. Because you are a rich dude. Okay. That is quite a bit of gold. Okay. Dreaming here. Let's wake up. All right. Any questions on that? All right. Now, before we move on, there's an interesting little concepts applied here. More kitchen physics. Okay. Consider the following information as it relates to metals of cooking pots and pans. It's easier to change the temperature of metals with low specific heat than it is with high specific heat. We saw that. Aluminum is not particularly, it takes more heat to heat up the same mass of aluminum than it does iron or copper or anything else. It is harder to change the temperature of metals with high specific heat, like aluminum. So look at the list of metals and specific heats in the table above and answer the following questions. Considering specific heat alone, which metal could be used for making practical pots and pans that are most energy efficient for use? What would be the most practical? Certainly the lowest specific heat in the table above is less than that. Gold. Is that practical to make your pots and pans out of gold? I don't think so. Okay. Next to that was?
Practical. That's it. Practical.
Yeah. Okay. So gold is not that practical. Don't jump up to copper yet. There's lead. Hey, why don't we make our pots and pans out of lead? Okay. A few reasons. I would have to unload the dishwasher every time then. I don't want that. That's not very practical to me. My wife wouldn't want to be lifting pots and pans that are made out of lead.
You get lead for it.
And you get lead poisoning, much more practical. No, let's not make them out of lead. Next after lead is mercury. Why don't we make our pots and pans out of mercury? What's that?
Concrete.
Okay. Why not mercury? Guess what? Mercury's a liquid at normal temperatures and pressures. They would not make very good pans, would they? Okay? They're liquid. They'd spill all over the thing. You couldn't cook any. And they're toxic as well. Okay? So mercury wouldn't be a good idea. After that is, finally someone said it, copper. Say again? Copper would be the best practical use. It's a relatively cheap metal, and it's, not as much anymore. It used to be. And guess what? Some of the pots you'll see today are copper bottom with stainless or something at the top. That's why, because it takes less energy to heat the pan and go from there. All right. And then, again, it says, well, I'll let you read the rest of it. We've done enough on that. All right, any questions on specific heat? Remember that formula, you'll be using it in the lab. And specific heat, by the way, is when you have the change of temperature. That's when you use specific heat, when you have a change of temperature. Remember, that's one of the results that you could have when you add heat to a material or take it away, a change of temperature. All right. Now we're ready to talk about heat flow. Now, just that term is indicative of the fact that they used to think heat was a material substance that could actually flow. We know it's not, okay? But we still use the terminology heat flow. 3 mechanisms for heat transfer due to a temperature difference. Okay, the first of these is conduction, the second convection, and the third radiation. Now the next 3 slides are going to talk about each one separately, so I'm not going to go into great detail now. But natural flow, get this again, they said it before, they're saying it again, natural flow is always from high temperature regions to cooler. Always goes in that direction, natural flow. You can sometimes force it in the other direction, but that requires energy to do that. Natural flow, always from high temperature regions to low. Okay, leave it a minute. Okay. So I'll start talking about these 3. Conduction. In general, conduction is only in solids, okay, which we think of our metals and things like that. They transfer energy through conduction, okay? Convection is usually fluids. That could be liquids or gases, and that's through fluids. Radiation can go through just about anything, but is most effective if it's going through space. Because radiation does not require particles to assist in the heat flow. In fact, they get in the way. So conduction is mostly through solids, convection mostly through fluids, which is gases or liquids. Radiation can go through anything, but its preferred medium is a vacuum. No material there at all. That's where it goes through best. So 3 very different media for these 3 types of heat flow.
We got the old radiators.
Yeah. Right. And yeah. Okay, that uses all 3 of them. The old radiators that used to be under the windows, it seemed like they always were under the windows. Conduction, the radiators were made out of metal, right? That conducted the heat from the hot water inside to the room on the outside. That was a conduction mechanism. Convection,
Believe it or not, those really work.
oh, they do really well. And what the radiators, remember, it's just like the radiators in your car, only on a bigger scale. They have various tubes running through them, okay, but airspace in between. That allowed convection to go. Cold air would go under the radiator, and then the warmer air, as it heated up, it would rise, and it would circulate through the room that way. That was using convection. Radiation, you could stand back from it and feel the heat off of it. That was radiant. Everybody got this so far? Okay. Let's go first to conduction. Okay, that's heat flowing through matter. Okay. The mechanism here is you heat one end. Now I'm going to go and show the thing here. Here we have a pipe. And this is a solid pipe, by the way. And let's say it's a metal pipe. Okay. And you put your Bunsen burner under that, you're heating one end of it. And you have a series of 4 thermometers there stuck in it. Let's just assume this is around room temperature, about 20 degrees Celsius. Okay? In a very short time, depending on what type of material the pipe is, this one's going to get hot pretty quickly. This one will get hot sometime after that. That one will get hot. That one, it hasn't quite gotten there yet. What's happening here? The hotter atoms here are bouncing into the atoms next to that. And they're bouncing into the next one and the next one. It's the average kinetic energy of the molecules is what makes high temperature rise. Okay, so that's what's happening. These are bumping into those and those and those, and these warm up first, these warm up next, these warm up next. These keep getting hotter, these keep getting warmer. Finally, these will start going up too. You'll see that happen. That's conduction. Hotter atoms collide with cooler ones, transferring some of their energy. Average kinetic energy of molecules, that's what temperature measures. Direct physical contact is required. Okay? You can't have a gap in between there and expect it to conduct. It won't. Okay? It cannot occur in a vacuum at all because there are no particles to bump into each other. So it will not work in a vacuum. Actually works best in solids. But not all solids. Okay? There are some very poor conductors. Okay? And if you think about it, again, go from the macroscopic to the microscopic. If those molecules are made up of big, old molecules, then it takes a lot of energy for this one to make this one move. They're just too big and bulky to do. If they're lighter weight molecules and have more freedom in their crystal structure, then they will translate it much faster. So, any of you ever cook with a Pyrex dish? Of course. Okay? And a Pyrex dish is technically a pretty good insulator, a poor conductor, a good insulator. It cooks the food very evenly because of that, and the food cooks basically from the top, rather than sticking so much to it. Mostly because of large, complex molecules. Okay. Styrofoam, a terrible conductor, a very good insulator. Wool's a pretty good conductor. Okay. Now this has nothing to do with specific heat. Okay, because we have specific heat of air. That's what reminded me. It has nothing to do with specific heat. This is how energy flows through it. Air is a lousy, lousy conductor. In the next slide, we're going to see it's a great convector. It transfers with that. So if you can make sure the air is still and not able to move, it's a great insulator. Where do we use that? Second? Okay, you're talking electrical type thing? Yeah, and we do there, so we'll get to that in the next chapter. Yeah, okay, there's something in between. But what makes, do you mind? What makes this a good warm coat? Yeah, the wool there. Well, what is making that? The wool is pretty good itself, but the wool traps air, dead air, still air, and that doesn't conduct heat at all well. Okay, that's why a flannel shirt made out of cotton will be better than a flat shirt. Whatever you call that material, but cotton material as well, because flannel has those little fibers that trap the dead air space, and makes for a great insulator. thermal underwear. Maybe made out of the same material as regular underwear, but it has the airspace in it. Okay? So, dead air. Those windows are not these. Okay? What kind of windows are good insulators? You know?
Double pane with the
Dual pane, yeah, that have dead air in the middle of them. Great insulators. Those are just glass, one sheet of glass. If you go back and see, yeah. So, and most of the time that gas in between, I think, was argon, which is a non-reactive gas. But that's beside the point. You want dead air in between them. And that's what makes it good. And what you put in your attics. Rock wool, and the older houses had a lot of that. We do in ours. Fiberglass, those kinds of things. And what's the advantage of that? Well, those are good insulators themselves, but what's better is they have dead air caught between the fibers. They're big, spongy like this, especially rock wool that hasn't settled down. It holds the dead air space, okay, making a great insulator. Okay. Here's what's happening to the molecules here. You add the heat here, really gets these vibrating. That makes these vibrate, makes those vibrate, makes those, and it diminishes down the line. If you leave it here long enough, they'll all be vibrating about the same. But at least initially, you have to do the closest ones to you, and then it works its way down. Okay, that's if it's a good conductor. A good insulator, these are going to hardly affect those next to it. Okay? And guess what? Air, they're not even adjacent to each other. So that makes for a great insulator. As long as the air can't move. Dead airspace. Okay, here are some sample conductivities. Okay? Were you through with that last slide? Okay. Sample conductivities. The very best conductor is silver. Okay? Silver is a fantastically good conductor of heat. Later we'll see it's also a good conductor of electricity. Okay? Now the reason is silver and a lot of your other metals have what they call free electrons. Okay? Those free electrons are very lightweight and easily mobile. So they'll just go back here. Whoops, wrong way. Go back here. Those free electrons can just transfer that energy like crazy, really, really quickly, making a great conductor. Whereas a big, bulky molecule of ceramic is not going to conduct well at all. Okay. Now, next after silver would be copper. They didn't put it in this table. I think in your book, you have more in your book. 4.3. After silver is copper. Really, really close to silver, but not quite as good. Okay? After copper was aluminum. They don't list that here either. After aluminum is iron. They really skip down big time there. After that is lead. They don't show lead here. After that is concrete. A pretty lousy conductor, which makes it a better insulator. And guess what? If you're sitting over there near the windows, you probably will feel the cool from the outside more quickly than you would sitting next to the concrete wall. And it's not just the glass. More than the glass is the aluminum. The aluminum is going to conduct the heat far faster than the glass will and way faster than the concrete will too. So it's that aluminum is hurting you. And I can remember when my parents built the house on the farm, the aluminum windows were just coming into play. You don't have to paint them. All that trim work, and painting is so tedious. Aluminum windows are going to keep their sheen forever. You don't ever have to paint them. But they were lousy conductors of heat, so those rooms would be colder than they would if it was wood frame windows. So we gave up one thing to get something else. Okay, water's a lousy conductor. Later we'll see water like air. If it's moving, it has something else going on. Styrofoam, a great insulator. Air is a great insulator, and of course, a vacuum is is the worst conductor because there's no molecules to move. So it's going to be a fantastic insulator. And where do you see examples of that? Do any of you ever carry a thermos bottle? You know what I'm talking about with a thermos bottle. Okay? Big bulky bottle, but can't hold very much. Why? Because either it has supposedly a vacuum around it, but if not, it has dead air space around it. And it's a really lousy conductor, so it keeps your hot coffee hot or your iced tea icy cold. Now, I don't know, we haven't looked into how they do it. What is the name of the thing now? I want to say Yeti. Those Yeti coolers, any of you have those, or Yeti cup holders? They're pretty good, aren't they? They really take advantage of these lousy conductors, great insulators. Okay.
You know, they used to be, I used to have one big old green one carried.
Yeah.
And inside was glass.
Yeah.
How
Okay.
they did that, I don't know.
Yeah.
They don't make those.
And another thing they did, if you noticed it, they silvered it, reflecting the heat back.
Yeah.
And also, because the silver would be a great insulator, but it's outside the glass, not against it, and it reflected heat back too. So that was a different.
I don't have one of those little.
Right.
minis, but
Okay. So that's conductivity. The next of those was convection. Excuse me. The next of those were convection. What did I say convection works best in? Excuse me. Liquids are gases. Fluids. Fluids are either liquids or gases. So this is energy transfer through the bulk motion of the hot material. Okay? Now, do any of you remember the old see-through pots and pans they called visionware? Really? Too bad.
Yeah.
Yeah, I thought I heard it too, but I was hoping it wasn't an accident. When I was driving in 2059 this morning, eastbound into Birmingham, I couldn't tell how many cars were involved in that. It had cars backed up forever coming this way, and that had been a pretty major one. I guess the rain on the highway, I don't know, but it's still happening, it sounds like. So folks, be careful driving home. Okay. So this is energy transfer to the bulk motion of the hot material. Okay? Remember, solids are in crystal structures. They don't move. There are various, microscopically, the free electrons or the molecules bounce into each other. Bounce into each other. That's how they conduct heat. But a liquid or a gas, they're free to move. So therefore, they convect quite nicely. Okay? Excuse me. Okay. Now, what are some examples of convection? We mentioned the radiators. The cool air moves underneath, gets heated up by the radiator, and then it goes out the top. That's the opposite of forced air heating and cooling. That's convective heating and
yeah,
cooling.
I thought convection oven.
Yes, and a convection oven does the same type thing.
I don't know what it works.
Okay. It has a fan forcing convection.
I don't know how it works.
Yeah. And supposedly they cook more evenly, not relying on radiation and conduction alone, but also forcing
You
convection.
see these little air cookers they advertise. They put
Right.
turkey on or
Right.
whatever.
Right.
It's got some heat in it.
Oh, yeah. Okay.
But
I don't know much more about it either. Yeah.
But anyway, convection.
Yeah, and that's convection. That's the movement of the hot material. Excuse me. That's the movement of the hot material itself. Okay? Your space heaters quite often do that. Now, if your space heater has a blower on it, that's forced. But and they do count that. But if you're blowing the air across the heating coils, then you are taking advantage of convection. Okay? But they will convect without otherwise. Now, The common saying is the natural convection mechanism is hot air rises. Now, why would hot air rise? Okay, because the molecules in air will bounce off each other with more energy as they heat up, because the average kinetic energy of the molecules is what measures temperature. And the hotter the temperature, the more kinetic energy, so they bounce off of each other with more force, with more moving each other further apart, and that makes them lighter. It does in some ways.
Hot air is drier than
Well, usually because you have,
just forget I asked.
yeah, actually superheated steam will do the same thing, and that's really, really hot. Okay, so but usually when you heat air, you dry it out, and that's why that happens there. But hot air rises. The other thing you may hear people talk about, is the chimney effect. It's exactly what a chimney does. You heat the fire in there, and the hot air goes up. Well, the bad news on that is most of your heat is going right up the chimney, okay, because the hot air is rising. But you get radiant heat off the fire this way. Good old scientists, that we don't usually think of them this way, Benjamin Franklin came up with a solution for that. You want to know what it was? A potbelly stove. Okay? He had the fire in the stove, and the flue kind of wandered around all over the place, and then the stove radiated the heat. It convected heat. It did a lot better job. Not all of it just going to. A lot of it still go up. So that's why a wood stove will be a lot more effective at heating than the fireplace, because it's in the room, and convective air around the potbelly stove or the wood stove will then circulate through
I
the
can
room.
remember when I used fireplace, if you was laying down in front with the kids and the front door was down here,
Yeah.
you could actually feel the cold air coming across.
Absolutely.
Right up.
Exactly. Yeah.
I mean, it's just,
All you were using was the radiant heat off the burning logs or whatever were in it.
most of it was loud.
Most of the heat
I've
was
got
lost.
one, I never used it.
Yeah, we've got one in our house. We actually have two. One was coal. Two were coal. We don't burn coal anymore, so we don't use those. But the one in the den, they put the chimney just above one story, where it's a two-story house, so it draws really lousy. Actually, air comes whipping over the top and blows air back down in, so it would smoke up the house, so we'd never use that one. That was a completely different reason. But that's convection. What I was going to say about the old visionware, that glass type pots that you had, you could see through, you could actually see the water circulating. The water would get hottest in the middle, circulate around, get cooler on the edges. You would see the water circulate like that. The hot fluid rising, the cooler one sinking. Okay? Same thing is happening here. Huh? It probably was. It was now Corningware is usually or what do you call it?
Pyrex or something?
Yeah, but you can't see through that. But these were pots and pans that were actually made out of glass, and you could see they're usually amber colored. They were only popular for a few years. I know my mom got some, but they didn't make it too well. But here's your radiator, and you see the what do you call those, flanges on them that allow more air contact. The cooler air goes underneath, just like you were talking about with the fireplace, only it's not out the chimney, it circulates through the room this way.
Flue?
Yeah, a flue would be the actual. Huh?
I thought you were asking.
Oh, flutes. Okay, yeah, okay, got it. Yeah. Okay, that's the mechanism for convection. Mostly works with fluids, gases and liquids. Okay? Now, here's the concept. I don't find this particularly helpful, but if you had same air in an imaginary box here, you heat up this box, but don't heat up this box, the air molecules get further and further apart. So the box expands, okay? But they still got the same number of molecules in it, so they're balanced, okay? But if you go back to the size box you have here, make a smaller box, it has fewer molecules in it, so this is heavier. The colder air is heavier per unit volume than the hotter air. And Tyler is here. Okay. Well, he was here. Where did he go? Oh, there he is. Okay, I see him. I hope that wasn't you that we heard the crash not long ago. Did you see it? Oh, okay. All right. Okay. Oh, let me also mention this. My grandmother and my great aunt, houses many, many years ago, had the furnace underneath the floor, okay, and had a grid at the top, and they liked the furnace, no forced air at all. The heat just rose. That was a perfect example of convection. Okay, no forced air. It all just rose right out of that. Of course, the room where the furnace was a very warm room. The other ones were quite a bit cooler.
It worked.
And it worked. It certainly did. Okay, the third type of heat flow, we might say, is from radiation. Now, radiant energy is energy associated with electromagnetic waves. Okay? Now, radiant energy is any kind of radiation. It doesn't have to be associated with heat at all. Okay? Like gamma radiation, that's radiation. It travels through space. It's deadly radiation. Fortunately, our atmosphere blocks just about all gamma radiation to keep it from coming to Earth. Otherwise, we'd be fried. Okay? And that's when you start wondering about, can there be life on other planets? Well, they'd have to have an atmosphere put together very similar to ours, because they can't allow that gamma radiation in, or people like us wouldn't be able to live there. Maybe other life forms could, but we couldn't. Okay? You also have light radiation. Has not much to do with heat. But anyway, any radiation goes through a vacuum. Travels best through a vacuum. They will come through atmospheres. They will go through liquids. They will go through solids. Radiation will go through just about anything, but it operates best in the vacuum. Okay? All objects emit and absorb radiation. Okay? Are you emitting any radiation right now? Yes. If you put a thermocouple real close to your skin, you find it several degrees warmer than it is out here, because you have an aura of heat around you. Okay? That's why those of you who have more covering on top don't need to wear hats. But those of us who have less, in order to trap the heat that moves through convection through our bodies, it goes right out of the top. Yeah.
80% of your body.
Yeah. I've heard the saying before. This was, I think, sort of in military, but it would be hunters or anything else. If you want to keep your feet warm, put on a hat. And it certainly will work, because if you have no hat, you're going to be radiating heat from the top, and your feet will then have less heat circulated through your body. Okay? Excuse me. Okay. So all objects emit and absorb radiation. The temperature determines how fast the emission is, the emission rate, the intensity of the emitted light, which is not quite the same thing, but similar to it, and the type of radiation given off, whether it's heat radiation or light radiation or some other type of radiation, even things like X-rays or something like that, which is, again, is a deadly thing that our atmosphere blocks that we manufacture down here on the needle. Now, the temperature is determined by the balance between the rates of emission and absorption. And they give a good example here, which for this author I found is pretty interesting. But I'll go back and come back to this one in a minute. Now, for those of you who don't have late afternoon classes, and I guess most of you automotive guys are here late every afternoon, aren't you? But on, say, on Fridays, for instance, for me, I work only usually a little over half a day on Friday because I'm here late Tuesday, Thursday, and Wednesday evenings, and a little bit late on Monday as well. So I get off a little earlier on Friday. Okay, if it's a nice sunshiny day, but even a cool day, like in the 40s, if I go out to the vehicle and get in the car on midday when it's been fairly sunny, what's my temperature difference? If I've had the windows rolled up.
The car?
Yeah.
It's going to be higher.
Many degrees higher. Toasty warm in there, 40 degrees outside and almost too hot inside. It could be if it's a bright sunshiny day. Where does that come from? What's happening there?
The car traps the heat.
Okay, here's what's happening. The absorption, the light comes in. Now that is normal light. Now I wish we had, let me see if they have it here. No, I don't think so. I wish we had the spectrum. Did we have that in our earlier chapter? The radiation spectrum. I said radiant energy can be any kind. Gamma radiation, X radiation, cosmic radiation, or light radiation. None of that is heat. It can generate heat, but none of it is heat itself. But the light that comes in through the glass on your windshield, okay, that light is electromagnetic radiation. But as it comes through the glass, it loses just a little bit of energy coming through the glass. So it drops its frequency. As it loses energy, drops the frequency, and becomes what we call infrared radiation, which basically is heat. So the light comes through the windows of the car as visible light, no heat necessarily involved there, but as it comes through, it loses just enough energy to become infrared, which is heat energy. Okay, that infrared energy then doesn't have enough energy to go back out through the glass again. So therefore, like you said, it gets trapped in the car. Okay? So the rate of absorption is greater than the rate of emission. Okay? So that's what they're talking about here. Now, what is that effect called? Have you ever heard the term for it? The effect of light coming in, heating something up, but then not being able to escape because it's lost enough energy so it can't go back through the glass. I'll give you a hint. Plant breeders use this a lot. People who are raising exotic plants in ultraviolet is doing the same thing. Okay, where do plants breeders raise their plants in the wintertime? Say again? In a greenhouse. Okay, using photosynthesis, but it's called the greenhouse effect. Okay? Okay, make sense? Yes, because the light comes into the greenhouse, it comes in, but then loses enough energy it can't escape, so it's trapped in there as infrared, which is heat energy. Okay? That's what they mean here. Our atmosphere kind of acts like a big pane of glass. Okay? It lets the light through, but as it comes through, it loses just enough energy, it can't go back out. Now, the compounds that are best at doing that are carbon dioxide, methane, and a few other elements or compounds like that. Both of those contain carbon. I don't know if carbon has to do with it or not, but they both do. So therefore, when we increase our carbon dioxide constituents of our atmosphere, we become a warmer planet. That's what they think is causing global warming. Huh? Okay, ozone is usually way up in the atmosphere. It may have some effect like this or not. I've never heard whether ozone contributes to global warming or not. Ozone, what it does for us, it's the layer that blocks those gamma radiation. Okay, that's why it's so essential for us.
We were losing our
Yeah, and we did. Does anyone know what made us lose some of our ozone?
Global warming.
Second?
Global warming.
No, that it probably has not to do with that.
fossil fuels.
Not fossil fuels. That has to do with global warming, because that's carbon dioxide and methane. Y'all use it in part of your auxiliary things in cars, because they're always changing what you use for it, trying to make it safer and safer. Second? Not gas.
Freon?
Freon, exactly. Freon was the first refrigerant that was manufactured a lot, and it's a, let's see if I can get it, fluorinated hydrocarbon, I believe it was. No, chlorinated, CFC, chlorinated fluorocarbon. That's what it was. Chlorinated fluorocarbon.
Chlorofluorocarbon.
Is what?
Chlorofluoro.
Yes, chlorofluorocarbon. Yeah, carbon. Okay, CFC. Now, what it did, as it leaked into the atmosphere, it broke down the ozone. When our ozone layer got thinner, more ultraviolet radiation came in. Ultraviolet, but also gamma radiation. If any of you ever saw the movie Waterworld, Kevin Costner, okay, remember those people had all sorts of growths on them and stuff and other things. Supposedly that was happening because the ozone layer was getting thinner. Now they made it seem like it was global warming, but the things sort of work together that way. So how many times have they changed the refrigerants in AC systems that you know about? So most of you are fairly young, so you probably only lived with one. But Freon is not used anymore. They went to R22 or something like that. What do they use now for refrigerant in AC systems?
R22A.
Is that right? R22A? Do y'all use it? Have y'all gotten there yet? What refrigerant do you use in ACs?
134A.
Second?
We use 134A.
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 Okay. Before that was 122A.
1234YF, that's what we're going to.
Okay, so
R12 in the 90s.
yeah, R12, and before that Freon. So they've changed it how many times? Always trying to get better and better. A better refrigerant, but also one that's less dangerous to the environment. And people have been very good about doing that when they knew what the results were.
R22 used to be
In houses? Yeah, right. Yes.
Does the volcano create more pollution than all of mankind?
They create a lot of pollution, whether it's as harmful as some of the stuff we do. I don't think they create any CFCs. I can't imagine that they would. They may do a little bit, but not much. But yeah, they create a lot of pollution. In fact, good question, Mount Pinatubo, I believe, was in the Philippines, and there was another one in Indonesia. And the years when they had major eruptions, we had not global warming, global cooling. They had snow in the northern part of the U.S. in June. Those years, because there was so much pollution from the volcanoes blocking sunlight coming in, that we had, they called that year the year without summer, because it was that much. Yeah, but most of that will clear out of the atmosphere over, it might take a few years or it might take a few decades, but it does clear out. What we're doing is not clearing out, it's actually getting worse. Okay. But yeah, you're right. They do pollute way worse than everything else, but it's part of nature and it sort of cleans itself.
That R22 was used in houses.
Yeah.
And I've got some of it.
Yeah. And it's probably still okay to use, but I think that,
No,
oh, it's not?
not for somebody like me that could hook it up.
Right.
You have to be trained.
Yes, exactly.
And the thing I was going to say is, the last jug I bought, one green jug, was like $35. And last time I talked to my buddy, he said it was well over $1,000.
Wow.
But you only, you have to be
Yeah.
you know, an electrician.
Yeah.
Because they have to capture the.
Yes. Capture the. Yeah. That's exactly why they don't want to get it into the. Yeah. And that's when an AC system does develop a leak, you change your system. You don't just.
I wouldn't have done that if I knew it was harmful.
Yeah. But
you can still buy that.
one household isn't going to be a huge thing, but thousands of households would. Yeah. Okay. Okay. So there's radiation.
Oh, that kind of freon
Yes.
that you can add to that. I forgot what my buddy called it.
Right.
But you can put it in on top of that also. If you
Right.
have that at your house.
I don't know what we use at our house. We have the trained professionals come in and do it.
Pretty good.
Yeah.
Save you, instead of a $2,000 bill, you could maybe get away with $1,000.
Right. Exactly.
That's where I think it's good, because my son's old.
Right. All right. The next major topic is 4.4. How are we doing on time? Right, here we go. Okay. We don't have much longer. Heat, energy, and molecular theory. Okay? We've been talking about this whole time. You know, energy can be kinetic, potential, mechanical, heat, whatever. Heat is a transfer of energy, and molecular theory, what's going on in the microscopic scale to produce the effects here. There's two responses of matter to heat. You've seen this in several previous slides, but this is slightly different from the rest. And this we actually did see in the last one. You can have a temperature increase when you're within a given phase. That could be a solid, you add heat, it warms up. A liquid, you add heat, it warms up. A gas, you add heat, it warms up. That's a temperature increase within a given phase. Heat goes mostly into the internal kinetic energy, making those molecules move more quickly, which is increasing the temperature. The measure of that is specific heat for that material. That's what we were just talking about. MC delta T. That's the heat that creates that. However, and we saw this in the last lab, if you remember, okay, well, here's the illustration of that. If you add more heat to a system, here we have ice, okay? Now, have any of you ever had wet hands when you reach into the freezer to bring the ice out of the freezer? And what happened? It stuck to your hand. And why did it stick? Because the ice was enough below freezing that it froze the water on your hands and stuck to your hands. It didn't melt in your hands, it froze the water that was in your hands. So if you add heat to really, really cold ice, it just becomes warmer ice, okay? You don't have a phase change. It doesn't start melting immediately. It's only when you get to the melting point, 0 degrees Celsius, 32 degrees Fahrenheit, the ice will begin to melt, okay? And when that happens, now you're changing phase. And when you change phase, no temperature change. We saw that in the lab last time, remember? We put the thermometers in and you saw the temperature drop, but then it quit dropping right around 0 and didn't drop anymore, even though the ice continued to melt. Because at a phase change, you have no change of temperature. Okay? The ice melts and soon becomes all water. Once it's water, you add more heat to it, the temperature starts rising. Okay? Or take more heat away from it and the temperature falls. Okay? Now, when it becomes a liquid then, you've broken that crystal structure of ice, and now the molecules are free to move around each other. But if you keep adding heat, and keep adding heat, and keep adding heat, you raise the temperature of the water, and raise the temperature of the water until you get to what temperature? 100 degrees Celsius or 212 Fahrenheit, which is the boiling point of water. And at that temperature, now you're freeing these molecules of water that stick close to each other and form a liquid to free molecules of steam. And they just fly anywhere they want to. While you're boiling water until as long as any water, liquid water, is present in the presence of the thing, your temperature is going to stay right there at 212 or 100 degrees Celsius. So therefore, if you're doing your own cooking and you get that pot of beans boiling, turn down the heat then. Cover it, turn down the heat. As long as it's boiling, it's not going to get any hotter, whether you turn up the heat or not. You'll just boil the water faster, but you won't make it any hotter. So therefore, turn it down. It's going to cook just as fast, and you won't lose as much of the liquid. Then if you lose all the liquid, then it will burn to the pan because it raises the temperature there. As long as there's water present, it's going to be right at 212 degrees Fahrenheit, 100 degrees Celsius. Okay? That specific heat within a phase, as the temperature changes, either as a solid, a liquid, or a gas, you can do it. In steam, once it's all steam, you can heat that steam to 500 degrees or something. They call that superheated steam. That's what they fire through the turbines at the electric power plants. I mean, that is hot, hot steam, and that's what goes through there. And you don't want any water droplets in that. You want it to be what they call dry steam. Okay. That's a temperature increase within a given phase. There you use specific heat. I can't get this to advance. Oh, here we go. It did advance. I just didn't know. The second of these, oh, there's necessity. All right, good deal. All right. Still missing Hunter. Oh, Hunter came in. I think I did see you walk in. I forgot to mark you. Okay. Jose, did he ever make it in? Not. Cody didn't make it in today either. And Zachary hasn't made it in yet. Okay. All right. The second of these is when you do have a phase change. I've already indicated, when you have a phase change, you have no temperature change. It's related to the changes in the internal potential energy. Because now, like I said, the crystal structure is breaking apart. There's no change of temperature there. You're changing the crystal bonding. Okay? And then the movement of the molecules, liquid molecules that like to stay close to each other, when you finally free those up, you're changing, again, the chemical bonding. That's called hydrogen bonding. You're breaking that. Okay? The type of heat we use for that is called latent heat. The term latent means hidden. That's a hidden heat. You don't feel the change, okay, because the temperature is at the same thing, but the change is occurring in the phase, okay? Now here's the what I was sort of waving my arms about. If that ice is below freezing, you add heat to it, you don't melt it. All you do is warm up the ice until it gets to the melting point, which is 0 degrees Celsius, 32 Fahrenheit. And at that point, you add more heat, no temperature change, but you're changing phase from solid to liquid. That's when the ice starts melting, okay? When it's all melted and you add more heat to it, then the water starts warming, okay? This is specific heat down here, latent heat here, specific heat here. That's why ice had a different specific heat from water, 0.5 as opposed to 1. Okay? You keep heating that, it warming up until you get to the boiling point, and at that point you have no temperature change. Constant temperature, but now the latent heat of breaking those hydrogen bonds to boil the water and free those water molecules, that's what's happening here. Internal potential energy is changing, not the temperature. Temperature is average kinetic energy. But once all that steam, water has changed to steam, now it starts warming again. And this warms at 0.48 calories per gram per degree Celsius. Water is 1, ice is 0.5, steam is 0.48. Almost the same as ice. Okay? So, specific heat, latent heat. Specific heat, latent heat, specific heat. Okay. Now those two latent heats are very different. And for some reason this slide set does not show you that. Okay? So let me give it to you. It's in your text. And here is the formula for latent heat. Q is equal to mL. That's latent heat, capital L, like specific heat was before. What's missing that was in the specific heat equation? The delta T. And why? You have no change of temperature when you're changing phase. So this is it. Now there's actually two forms of latent heat. One is called, there's actually three, but we're only going to talk about two. The latent heat of fusion, which you can think of as freezing, changing from a liquid to a solid, or melting, which is solid to a liquid. But that's called the latent heat of fusion. The other is latent heat of vaporization. That's changing from a liquid to a gas, or a gas to a liquid. We call those the same. Now, for water, which is our most common material, the latent heat of fusion is 80.0 calories per gram. Did I leave off degrees Celsius? No, it's not in there. There is no change of temperature. It's just calories per gram. The latent heat of vaporization, however, is 540.0 calories per gram. So there's where the biggest amount of heat goes, is in vaporizing something, especially water. Okay, so 80.0 calories for latent heat of fusion, 540.0 calories per gram latent heat of vaporization. Now this is also what, when it's coming out of going from a gas to a liquid, you were asking earlier about does water contribute to anything? And I wanted to say this, but we hadn't gotten here yet. Okay? Here's the answer to that. Have any of you been out in Arizona in the summertime? Ever?
Yes.
You have?
Yes.
What was different about it?
Well, they call it a dry heat.
Yeah.
But it's hot.
It is hot. Okay? But did you ever experience any, say, 90-degree heat, the temperatures out there?
106.
Okay, I know. Yeah, okay, but 90 before it got to 106. It probably felt cooler than 90 degrees here. And it's not just by comparison, it's the fact that we have so much water vapor in our air that is latent heat that we can't get rid of. Out there you can sweat and it evaporates right off your skin. You probably don't even realize you're sweating. But with all the humidity we have here, there's no place for that to go. You see, we are kind of like your cars. The mechanism we have to cool ourselves is water. We secrete water, and hopefully it evaporates away, and that cools us. You don't want the water evaporating out of your radiator. You want it just, doing it specifically.
Experience. It's waiting your mother's or your wife or somebody's cooking biscuits in the oven.
Yeah.
And open that door.
Oh, yeah.
That's what it's like.
That is exactly what it's like, and that's because all that water vapor is there in the air, and we call that the heat index. The higher the water content is in the air, the less you're able to cool, because you have nowhere for the sweat to evaporate, because the air is close to saturated. So you just continue to heat up, and you can have heat stroke because of that. Now you can have it in dry heat too, but it has to have higher and higher temperatures. You can have heat stroke here at 80 degrees probably, because of all that moisture in the air. And a lot of early season football games, now they've started pausing the games and letting the teams go over and cool off, because they don't want the kids, especially high school, they don't want them passing out, that kind of stuff. Okay, so those are the latent heat, and those are the formulas for it. The what? Q means heat. Heat, yeah. And you notice it's measured in calories. because the mass is measured in grams. The grams will cancel out, and that leaves you Q in calories.
Well, I see it's here in the book.
Right. Okay.
Somewhere.
Right. All right. We're awfully close to stopping, aren't we? Didn't I say we would stop at? What time is it now?
5:20.
It is 5. Okay, so we are past our stop time. There is a little blurb on page 103 on passive solar design. I guess we'll hold off that one. I wish we had time. Can we take time to do these examples, because that will be helping us when we go to our lab. So let's do this one example, but it's multiple parts to it here. Okay? There is a great table in your text on page 104 which shows for water your specific heat for water, ice, and steam. It shows the latent heat of fusion and the latent heat of vaporization. It also gives you mechanical equivalent of the heat, which transfers that to joules, from calories to joules, and vice versa. So let's do example 4.7. So let me find, here's a good place for it. Okay? How much energy does a refrigerator remove from 100 grams of water? 100.0 grams of water. Okay? Now what's that a measure of? That's your mass. Okay? That's water at 20 degrees. And what's 20 degrees Celsius, approximately? Room temperature, exactly. So that's water you just ran out of the spigot, and you're going to put it into the ice tray and make ice at negative 10 degrees Celsius. Okay? So what's the first thing you've got to do to that water at 20 degrees Celsius? What's the first thing the freezer does to it? Does it start freezing it immediately? No, it has to cool it down to the freezing point. It won't freeze before it gets to the freezing point. So the first thing you're going to do is cool the water from 20 to 0. And what formula would you use then? The question is, how much energy? And what do we measure energy in? What symbol for it? Q. And when you're cooling, I'm going to call this Q sub C for cooling. What's your formula? Cooling means change of temperature. MC delta T. What's your M? That's your mass. That's the 100 grams. Perfect. Okay, what's the C for liquid water? 1.00 units. Oh, and that's grams. I forgot to put my grams down. Calories per gram degree Celsius. And then what's your last? The delta T? 20 to 0 is 20 degrees change of temperature. 20 degrees Celsius. Okay? Notice the grams go out, degrees Celsius goes out, and that gives you 2,000, isn't it? Yep. 2,000 calories, or 2 kilocalories. That's to cool the water to the freezing point, right? But then you've got to do what? You've got to freeze the water. So this is a Q due to freezing, or that. And what's the formula for that? ML sub F. That's the latent heat of fusion, which you can think of as freezing. ML sub F. And what's your mass? A little louder. What'd you say? Yeah, it's still the 100. 100 grams, 0.0 grams. And latent heat of fusion for water? Latent heat of fusion for water, right there on the page. This page, on the board. 80.0 calories per gram. Oops, I just went off this thing, so let me pull this back. I can't close my parentheses. Oh, there I did. That's a calorie there. You can't read it, but it's there. And what does that add to, or multiply to? 8,000 calories. Only 2,000 calories to cool the water 20 degrees. 8,000 calories to do that same, not cool it a single degree, but to change it from water to ice. Phase change. Okay? And then what do we do? It says ice at negative 10 degrees Celsius. So what's the next thing you do? This is cooling the water. The next cue here is cooling the ice. You have to cool it from 0 degrees, the freezing point, to minus 10, because that's what they said. It's going to ice at negative 10 degrees Celsius. Okay? So what is your formula for that? Anytime you're cooling, you're changing temperature, so what formula do we use? No, that's freezing or changing phase. When you're changing temperature, what formula do we use? MC delta T. Now what's different here? The M's the same, that's still 100 grams. The C is different. What's the C for ice? 0.500 calories per gram degrees Celsius. Now, I'm running out of room. And what's your delta T? It's going to 10. The change of temperature is 10. So that'll be 10 degrees there. Okay. I'm sorry. I just ran out of room there. Let me write that over here. Q, change of temperature for ice is MC delta T. That's 100.0 grams. The same mass we had. Your C, specific heat, was 0.500. Go back to your table there, just on that green table right across the column there. Ice is 0.500 calories per gram degrees Celsius. Okay? And then your change of temperature was 10.0 degrees Celsius. Okay, so the grams are going to cancel out, degrees Celsius cancels out, and that leaves us with what? 500 calories. So how much heat was required? 2,000 to cool the water, 8,000 to freeze the water, and another 500 to cool the ice, 10 degrees. So that was a total of 10,500 calories, or 10.5 kilocalories. Okay? Okay. Now they change it all to scientific notation, which is fine. Well, they don't quite do it in scientific notation, but it's fine. Okay, I think we'll stop there and pick up next time, if I can find my pencil here. Here it is. With evaporation and condensation, which sort of follows what we were just doing. And that will be these phase changes. Oh, and there's where it picks up. So we'll start next time there. We'll have a little review there. All right, any questions? Okay, sorry we ran a little over, but I wanted you to have all this because we are going to need it in lab today. Okay? Okay, I forgot to turn on the microphone for the first part, but we'll do it for the second part here. Now, on the back table there on the left-hand side, you will see, you'll see some empty cups stacked up there, okay? If each team will get one of those cups, now only two can do it at a time, so two do it and then move out of the way for the next two. Okay, first thing, zero the scale before you do, well, no, I'm sorry. Put the empty cup, if there's any water in the bottom, dump all the water out, okay? Then put an empty cup on the scale and 0 the scale with the cup on it. Okay? Now, over here, the covered cups, these are filled with water. Okay? So what you'll do, as soon as you 0 this one, okay? Okay. So, there's 4 or 5 cups there, so you have some spares. Put the styrofoam, one of those empty styrofoam cups on the scale. 2 teams can do it at once. 0 the scale and pour water from these cups that are covered until your cup on the scale is maybe right at about half full. Maybe a little over, something like that. Okay? Record the mass of the water added. Then take the cup off the scale, cover it, and bring it back to your station. Does that make sense? As soon as you've gotten the mass, cover it and bring it back to your station. I'll tell you what to do next. Okay? So 2 teams will go on and start that. Get an empty cup, and 2 people from, y'all are from the same team, aren't you? Okay. 1 team there, 1 team could be with this other scale. Okay. Good. Okay. I'm holding your nose on. Good. Okay.
But they was on that side. And I still get it.
All over.
None of that mechanic, big man bullshit. But here, I'm like, hell no. So big. I'm just saying, like, it's just 2 minutes mechanic. I get around 170 or whatever. Now, it was nothing but
Put a thermometer in it so you can determine its temperature.
It's ghetto. If I'm ghetto, imagine if I was surprised if you looked at pants and there was a gun inside the pocket.
It's in there, whatever you got in it, off the house, please. As soon as you get the temperature, turn it on. All you do that there, put the cup on, 0 the scale, and pour it about half full of water.
I hated it because I want to go to my home. I don't know why. But then I'm too crazy for a white student. They're going to keep my business. I said, this is that expensive. And I remember this class was big expensive. People that didn't do no work. I say best seating, I say do no work. Who can say I was the best seating? Best seating, who ran the store? No, it's the new building, not the old.
Okay, all teams have done your, got your temperature. You got the mass of the water, that's number 2A, right? And then you've got the temperature of the water, that's 2B, or not. Okay, now, flip the page over, place another styrofoam cup on the scale, an empty one by the way, okay?
I can put 30 pounds.
I've got to get it around the bar, sorry. Got to get it out.
I'm saying, is that they cookies? But my fat ass just seeing shit. Really, I've been eating at the period. Well, I got my salad, but I took an appetizer dresser, so I'm not really hungry. And I got a headache, but I ain't gonna eat shit. Really? Don't be like me. Don't eat and lay down.
Okay, sorry, I forgot to get these out. I had to leave them in there. By the way, once you got the temperature of the water, cover that cup so it doesn't go down much. Okay?
Cover what cup?
Oh, so 0 that
I didn't
cup,
see that cup.
and then place just a few ice cubes. What does it say
Yeah,
over there?
moving fast.
Okay? Put enough to make about at least 50 grams. Got it? Okay. Record that. At least 50
Is this the 700? I can't.
At least 50.
But it's empty.
Okay, yeah. Empty cup, zero it. Okay. Now, once you've done that,
This ain't the braided bunch. It's the
then put the ice into there. You've got the mask.
I should
Put the ice into there
I put Dustin on the now.
and cover it again. Okay. Yeah.
It's like you can't watch it now for free because it's
Record it.
on air, but you can watch clips of it on YouTube. It's nothing but fighting the other night from. It's like
Okay. Have all teams done that?
I know love in hip hop or the Real Housewives of Atlanta. It's like those.
Get at least 50 grams of ice. Huh? Yeah, yeah. We'll put the thermometer in it, but you have to wait until all the ice melts. You cover it again.
Like, try to show me because I'm going to put it in the water. I'm not going to go on ABC Thursday morning and cry my eyes out because it's like, you made me feel so bad about myself. This is what it I looked at the name of the box.
Okay, and cover it up. Oh, no problem. Play with me.
Hit the student.
Okay.
Then it was, girl.
All right. While we're waiting for the ice to melt, do all the teams have that part done? Okay, leave off with the if you recorded your math, put it in and cover it with the thermometer in there. Okay? No, put the top cup over the thermometer. All right. So we've insulated it as well as we can, right? Okay. You can leave it covered. Is all that I can help?
60 grams.
Okay, leave it covered. Okay, let's go do the part 4 at the bottom, production. Everybody come over here. Okay? Leave your things covered. Okay? And come over here. We're going to do production here. Everybody? Okay. Now,
My leg.
by the way, folks, don't mess with anything else in the lab because it may be experiments in progress or whatever. We don't want to break anything or damage anything. But here, this is our stuff. You can play with this. Okay? Here you'll see a number of, well, first, would you read the temperature off the scale there? In the room. Okay. No, the room temperature is, oh, that's that one. Yeah, the room is 68. Okay? The room is at 68 degrees Fahrenheit. Okay? These pieces of plastic and metal have been in the room for at least an hour or more. So what temperature do you think they're at?
68.
Yes, they're both at 68 degrees Fahrenheit. So estimated temperature of the metal, Fahrenheit. And plastic? Okay? Then come over here. Don't go back anywhere. Hey. Oh, you did it. Okay. Yeah, bring the lab sheets with you. Okay. Yes, because we're in the room. Equilibrium with the room. Okay, now, pick up one of each. Okay? And hold them to a facial sheet. Okay? You don't have to hold it that long, just long enough to tell which one you feel like is warmer and which is cooler. And record that. So each of them next to your facial sheet and tell which one feels warmer. Okay? There's a lot of them there. Go over and do it. Make sure they're not lying to you.
Which one warmer? Oh, true.
What you feel? Did y'all do it?
I know what it
You sure you can trust it?
Thermal conductivity, wouldn't that mean like
I don't know what this half solution is looking at. Excuse me, Hillary. Oh shit, so they were outside.
Okay. Are any of your favorite football teams, high school team or whatever, still in playoffs? Any of you? Okay. Well, have you ever been to a late season game? And okay, let's not play with the stuff, please. Let's not play with the stuff. Okay. Okay. But have you ever been to a late season game and there's one set of old wooden bleachers here and another set of really nice new looking aluminum bleachers? But it's late in the season, very cold out there. Which one would you choose to sit on? Why?
Because metal holdings in your
They're the same temperature. They've been out there for days, for years. They're at the same temperature.
now.
Okay, you're absolutely right. The metal conducts the heat away from your skin, whereas the plastic is a poor conductor, a good insulator. It comes pretty quickly to your skin temperature. So very quickly, when you put those against your face, you'll feel the plastic feels close to your skin temperature, which is maybe 90 degrees Fahrenheit, but the metal takes the heat right away from your skin and leaves it feeling very close to 68 or 70 degrees. So that's why it's a big 20-degree sensing difference, but they're really the same temperature. Because the plastic is a good insulator, the metal is a good conductor. The metal conducts your heat away, you feel the 68-degree temperature, or 70, and the plastic doesn't conduct the heat away, so what you feel is probably 90 degrees Fahrenheit. Does that make sense? Yay or nay? Okay. Now, check your iced water to see if all the ice is melted.
Now you know.
Is there any still in there? Okay. Then measure the temperature of the iced water. Is there any more ice in your glass? Okay. All right. All the teams that all your ice melt? All of it. Did it? Okay. Did you measure the temperature of the iced water? Okay, we're ready for number E. This is 2E. There was no 3. I don't know what happened to 3. 2E. Write the equation to determine the heat loss of the original water. That's the water from A and B. The heat loss of that water, and determine the heat loss. For what equation would you use for the water of A and B in the back to the iced water, which is B?
Can we just build the solar system?
What's that?
I want to build the solar system. Do you know how to do it?
Does anyone know what equation we would use?
Q
equals what?
MC delta T.
MC delta T. That's for a change of temperature. Your water changed temperature. What's your delta T? The difference between B and D, right?
Yes.
Okay, that's your delta T. What's your mass? That's the mass of A. That's the warmer water that you had there dropped in temperature. Its mass, which was A, times the delta T, which is difference between D and B. And then what C do you use? What is C?
Oh, Q equals water. Q C is water.
Okay, yeah, that's all water.
I was going to write this water.
1.00. What units? Calories per gram degree Celsius. What was your mass measured in? Gram. Both masses in grams. And your temperature was in degrees Celsius. No. It's just the water that lost heat. That water reduced in temperature. Just that mass A. Okay, does everybody see what that question was about? The water that was in A, that dropped down to the temperature in D. Just that mass of water. Okay? Just that mass of water. Okay? So did you calculate your heat loss of that water? You calculating now? In calories, because your grams will cancel out, degrees Celsius cancels out.
Calories.
Everybody do it?
Everybody supposed to build the solar system.
What's that?
They went from 30 to 70.
30 to what? I'm sorry.
Well, if you come to class, you might be able to understand what we're saying.
I read the book.
Oh, I was looking at the copy.
Well,
but
absolutely,
it
I
says
read
that
well.
SEL. Yeah.
I was six numbers.
Okay. So everybody got it? Now, every team should have a different answer, but just give me about what your answers are. Ballpark. You want got it yet? That's in calories. Right.
What's that?
That's what it is. That's the
No, those are calories. Okay. What's that? Yeah.
Okay. What's happening with the 19
Shoot on. I was following the smart.
1,000. Yeah. Well,
I ain't saying I ain't following this. I don't recall.
okay. Yeah. Forget that. We're measuring the grams. We don't go use grams. Okay. Little C calories. Okay.
But I don't know.
So you got a question?
Oh, look, you got that good game.
Heat loss is not in degrees Celsius.
Oh,
That should.
you did.
Yeah, you use the formula. I wrote the different formula. The 19 was that the difference in this one and the other?
Yes.
Okay, that's your delta T.
Okay. For the math, you don't use it.
How do you use that one? Okay.
Okay.
Again, quick recap, bud.
Times 19.
Okay.
35 times
Number E, excuse me. Number E, the equation was Q is equal to MC delta T. Right? Now, the M was the mass from A. The mass of the water from A on the front side. The C is 1, but it's calories per gram degree Celsius. The delta T is the difference between B and D. That's your change of temperature. Okay? Now, if somebody got a Q of mass, a heat loss of about 1660, that was reasonable. What did y'all get? 1506, that sounds reasonable. That's a little C calories. Put CAL. Okay? What did y'all get? Woo!
So how is it supposed to help me get my degrees for the thing?
That's going to have to be in
21. What do you get?
I'll get like 15 numbers.
Oh, 290, which is almost 3.
Right.
Hey, yours are a
My
little.
slipper get my clock. Man.
How did y'all
Look, I told you it's legal. It got gas. Alabama needs to stop playing and make it legal.
Yes, sir.
How America gonna count the people to
83 times what?
why the hell would y'all choose to take that? I was
Actually, yeah.
I've already
for true. Because I was gonna you remember the first part that I was
I'll say like this chain up.
Oh no, you can turn it. I'm be stuttering and this is not what I'm
Yeah, that looks good. That's what I thought it was. Let me see.
So I erased the 35.
Okay. Your math.
So it's right.
Here's where I think it messed up. Your math is 83 grams. Could you come show me on the scale about what that was? It doesn't have to be the same. For about the same amount of water you had in the
Oh, it should
I
be
think so.
60 then?
Right. How? Did you? I mean, pour it in. Just get it out there.
Here's what I wrote.
I think you want to pour it in the sea.
I'm still pretty out of my I was so used to fights. I was like, now I share my family. I had 2 to 3 fights in my home so far. And I lost only 5, so I'm gonna stay.
All right.
And the ones I lost, I deserved it.
All right. That's why I thought that's way too small.
Not like a bullet bill, but I'm just like, I ate that.
What did y'all get?
I killed this one person and the police officer and tried to stab him.
360 grams. That sounds reasonable. Sounds what you think.
Police station, I knocked on the door because I'm like,
40 to 8 games.
but they never came to the door, so I just and I was like, y'all gonna jump in? Because I had my blade just because they was gonna jump in. And then I know it's a one-on-one. As soon as he said one-on-one, I started swinging. I know how you have to get me. And we was in public. I'm not gonna lose. This was embarrassing. The fights I lost was about 500. I lost 2 fights and won 2. Then I lost a fight as boys and girls, but I won a fight there too. Yeah,
What did y'all get?
665.
I don't think so. What's your math? 35 grams? Okay, come back here. Whoever did the measurement of the water.
You didn't say it out loud. It's for the whole class.
I think I know.
This shit nice as fuck. I'm gonna get one of my nerd friends to hack his system and delete the shit. But we should still use the laptop. I can answer it. Free package out. What you made, girl?
You broke down. Okay.
I like that.
Yeah. Use what you did.
I got 3.1.
65 was last you did.
So you made the big.
After 6.
If you think you got about the same.
Now, if I pass math school for B, my GPA will go up.
Okay.
That's why we don't do that.
We on chicks with
So
blue.
everybody has a number greater than 2,000, right? Okay, good.
True, it really is.
Now, number F. Ready for F? Okay, write the equation to determine the heat gained. Okay, excuse me. Okay, there are 2 heat gains here. What's the first thing that you did when the heat gain happened? You put ice into the warm water, right? What does ice do? Melt it. So the first thing you're doing is the melting of the ice. So that's going to be F. What is the equation that you use for the melting of the ice?
It equals MLF.
Okay, Q is equal to MLF, where LF is what? Second? I can't hear. Yeah, I know you got your mouth.
Lenient.
What?
Lenient. L-A-N-I-E-N-T.
What's that? Latent heat of what? Latent heat of?
Yes.
What's L? Melting ice, yeah. It's called latent heat of fusion. Okay? And what is that value?
One here only has the water.
What's that?
On this one has water. It's the same 80.
Yeah, wait. Latent heat of fusion. Okay, yeah. It's when you're freezing water. It's the same as melting. That's it. 80.0. Okay? The latent heat of fusion is 80.0. What units? Calories per gram. Now, gram of what? Your ice. What is your mass of your ice? Number C. Whatever that was, multiply by 80. And see what you get.
It's 348 times 80.
Everybody got it? What number did you get? Okay? So everybody has F done, right? About what kind of numbers you get?
4800.
Okay? So that's reasonable? Okay. Should be 4,000, 5,000, 6,000, somewhere in that range. Everybody get it? It's the mass of the ice times the 80. Yeah, mass of the ice times 80. What masses of ice did you use? 60. Okay. I thought you said 16. I thought that was very small. Okay. Everybody got the F done. Equation and heat gain melting. What was the other heat gain involved here? Okay, the ice is melted, but it now is water at 0 degrees. You have to warm that water, only the melted ice water, to the final temperature. Okay? So what equation do you use for that? Second? MC delta T again. Okay, what are you doing? Let's turn it off. Everybody got it? The equation for G is the same as the equation for E. Excuse me. The equation for G is the same as the one for E, only we use different numbers. What mass do we use? Not the mass of the water. The mass of the ice, because the ice melted to 0 degrees and then warmed up. What temperature change do we have?
0 to 15.
Okay, yeah, whatever your D temperature was, it went from 0 to 15, or whatever it was, 0 to whatever D was. So that, the answer to D is that. So you multiply that. Now what C do you use? No, because it wasn't ice warming up, it was melted ice, which is water. So you still use 1. Specifically to 1. Okay? Sounds reasonable. Sounds very reasonable. Okay? Okay, y'all got it? C is 1. What does it give you? How are y'all doing? Okay. Okay. All right. Some teams have already moved ahead. Let me check this one more team. How did y'all do? That's pretty good. Okay. Now, excuse me, you notice that you had two heat gains. F and G were both heat gains, right? One from melting the ice and one from warming the ice water. So add those two together, and that's your total heat gain, which is H. Add F and G together, that gives you H. Okay. Everybody got it?
Turn up. 35 days straight? 35 days straight? Oh, I'm like, hold the phone up. I'm going to get a break in between that.
And then add your answer for F to your answer for G and get your total heat gain. Has everybody done that already?
Girl, I come up with excuses. Oh, I broke my toenail. Still ain't gonna break it down.
How'd y'all do? Now, if you got your answer there, that's yours. How did y'all do?
I'm ready. Are you gonna take it?
I think I've seen them all. Okay. All right, listen up. Listen up. I compare the heat loss from E to the total heat gain from H. Okay? Find the difference there. Heat loss from E and the total heat gain from H. Find the difference between those two. Has everybody done that? Okay. How does that compare to your other numbers? Much smaller, right?
Yes.
Was it? That's nice. What was yours? Okay. And the others were in the thousands. 390. Okay. Now, if you want to do this, you can. This is just tell you how good you did. Take that number there, the difference, and divide it by either the total heat gain or the heat loss, either one, and just see what kind of number you get. You don't have to. There's no place to write it down, but just tell me what you get. Should be a pretty small number.
I'm saying, I know.
1.5.
I lost the state.
Really good. Okay. Now, which was larger, your heat gain or your heat loss? It may differ from table to table. Your heat loss is great. Okay.
I put a T in my loss.
Okay, so write down the heat loss. Okay, now we have to figure out why. Now, yours is so close that it may not be.
I was sure need to I was sure need
Temperature was this. Low room temperature.
I guess I could have started with a time.
Not much.
I'm sorry, I can't come on time. 4 hours or something.
Okay. How did y'all do?
You can ask him. Wait, y'all took the class with me. I never came on time. Really?
Yeah, that's just about me.
This morning? Yeah.
Yeah, like,
By the hospital?
yeah, I was like, when I did turn in, I was got stopped. There were already people trying to go in Uber, and I was like,
So you didn't see it happen?
I didn't see the actual impact, but I saw them like still rolling.
So who do you think was in the wrong? I feel like the silver crop was in the wrong because the black crop was hidden from the side. The black crop turned on the red turn and the silver crop hit, okay?
Did you do your fraction?
Yeah, so I think the black crop would be in the wrong.
I don't know, I was turning, it's supposed to roll up.
0.0.
Skirt.
I know, I was like,
Right at 6%.
I had a
Right, anything less than 15 is good.
I did it like,
So, why? Okay, here's probably why. Your heat loss, look at this, your final temperature was well below room temperature. You probably lost some heat to
I like that shape, but not the suits. When I go to weddings, I dress down.
He just said,
Okay.
sure.
Because I got stuck.
Go to. How did y'all do on yours?
So the reason why is the excess heat.
Yeah, it was that extra bit, and it wasn't much. It was like 6% or something. Okay, what was your why? Okay, your heat loss was greater with the final temperature, less than room temperature. Room temperature was around 20. You're at 17, so you probably lost some heat. All right. How does this seem, folks? Was it instructive or just busy? Was it instructive or was it just busy? Okay, you did. Okay, if you're through, I can take your class. I'll see you out of
So basically, he was lost to the
Interesting. I did come in sometime during my office. On Tuesday, Thursday.
So you gonna take later?
Yeah, Tuesday and Thursday is on the west end of the street. And Wednesday,
So I gotta go to the second test.
2 to 4. And Fridays, I'm on the Birmingham campus. Yeah, the chapter 3 test is on that.
That's fine.
What's that?
Add value to it. Yeah, it would.
Okay. Going back to the classroom.
10-4.
And we'll have a test from chapter 3. What's that? Okay, I'll take care of that. Appreciate it.
You the volleyball girl?
No, I got I was
I was trying to keep up with
Yes.
Okay, so 2 to 4 is from here tomorrow. I have to leave right at 4.
Like when the commissary give out water. Yeah, if you do like one drop, like I drop, they make them shoot. And you know, if you do 2 drops, I drop,
Okay.
kill them.
Yeah, my office is 55.
But
And I have lower down shot. Almost into the hole.
a little bigger than that.
Okay. If you're not finished, you can bring it on to the classroom. Sure, okay. You want both of them that day? Okay. You already did the second test. 2 and 3. Okay, well, I'll be in my office. I have to take them to both of you campus for her.
I was in the
1 and 3.
I was in the hospital for 2.
Yeah,
I had walking
Okay, y'all still working on it? Okay, well, I'll take it. Up to you. Huh? Oh, yeah. But, yeah, if you want to hang on to it, you can. I was just trying to keep